In Unit 5, Section 3, called Concentration Changes Over Time, the goal is to be able to find the order with respect to a reactant, the rate law, the integrated rate law, the value of the rate constant in the unit, and even something called the half-life and concentrations at a specific time. What's different about this section is you're going to use graphs to find some of the things that we found before using a data table. Whereas this time around, our goal, again, is to still take a rate law and find the order with respect to that reactant, meaning the exponent x, find the actual rate law and the integrated rate law, so that's new, and then also the value and the units of K. Also, we can calculate something called the half-life and any concentration or any time at a specific point in that reaction. So for these boxes here, there aren't really graphs that would go with it. You can just sort of skip it. The first graph that might be given to you in any of these kinetic experiments where concentration is changing over time is literally that, the concentration on one axis and the time on the other. And I've made some colored points on purpose, so like a blue and green dot I'll talk about as the video proceeds. So your first graph that you might get could be linear. And if that's the case, that if you have some data and when it's graphed, it's already a y equals mx plus b linear graph, then you know that the reaction is zero order. So either you will be graphing the data or somebody else, or the problem will be giving you the graph. But if it's linear, immediately it's zero order, which means then up here in the exponent is a zero. If you graph it, it's some kind of curve. You really can't decide if it's second order or first order because the slope of that curve or how steep the curve is not something you could just make a guess. So what scientists and mathematicians have done is take the natural log of all of those values and then compare it to time. And if that's a straight line, then it's called a first order reaction. And we won't really be covering the mathematics that prove that this works. And then if it isn't a straight line, maybe it stays as a curve, you'll regraph that data one more time, but take the reciprocal of all your concentrations and graph it compared to time. And if that's a straight line, then that indicates that it is a second order reaction. And so again, where you have a straight line is where you're going to decide if it's zero order, first order, or second order. So that's why those graphs are very important for you to have right at the get-go. And either you're going to make them or you'll be given those graphs. All right, so the next thing that you'll want to do is then be able to write the rate law for that reaction. And I just did a basic reaction with, reactant A turning into products B and C. So the rate law, I'll show you what the rate law would be for each one of these if it was zero order. So the first thing would be if it was zero order, your rate law would just be rate equals the rate constant K, and then the concentration of A to the zero power. But many times you'll just see that substituted in as just rate equals K because anything to the zero power is 1. If for some reason the data that you were given, and it's a linear graph when you graph the natural log of all your concentrations, then the exponent would be a 1. And whether you want to put a 1 or not, I would. But sometimes they maybe just wouldn't even have the 1. But I would recommend doing that. And then if you had to graph it and it was still a curve when you graph the natural log, then you could regraph it again with the reciprocal again of all the concentrations. And then that would mean that the A concentration is squared. Just going to fix that bracket. And again, this is a lowercase k. You're going to talk about capital K when we get to equilibrium constants in Unit 7. So that's the first thing that you can do. So if you have the graphs given, you just have to know how to associate the graph with the respect of the order of that reaction. All right, next would be what's the rate constant? Well, the one thing that also is helpful about the linear graph is on the linear graph, you'll have a slope. Okay, so I'm just going to put that in blue. And the slope of this graph is going to equal the negative, meaning that the slope is a negative value because it's the way it's heading down towards the axes. But the value of K is not negative. So be really careful that the slope is negative K, but K is never a negative number in this case. And then the same thing would be true here for first order, is that the slope of this graph is going to be same thing, negative K. But again, the rate constant is not negative. It's just the slope is negative. And then last but not least, if it was second order, the slope again here would just be k, and a lot of times then you won't have the negative because this is heading in the positive slope direction. So in the problem, either you will be told the slope and they won't tell you that it's the rate constant, or if you have to graph it, then you would have to find the slope of that graph using a graphical program or on your graphical calculator or graphing calculator. So the value of the rate constant, it is just the slope of the graph. Just be careful that, so I'm just going to say slope of the concentration versus time graph, whereas this one is going to be the slope of the natural log of A versus time graph. And then this last one, it's the slope of the 1 over the concentration of A versus time graph. And then the units, it's up to you. You could, again, derive the units like I did in the other video for 5.2, or there are a lot of students that would just prefer to memorize the units. Now, to be honest with you, I'm going to give the most common units, but I'm also going to rewrite them as what they could be if they weren't the most common. So the units of K for a zero order are molarity per second, which means moles per liter per second. But to be honest with you, I would recommend writing down that it's really an amount, meaning moles or molecules or some particle amount per volume, and your volume could be a centimeter cubed, decimeter cubed, you know, who knows, and then seconds or time. Now be careful, like sometimes it might be hours, it might be minutes, could be days. So I would actually recommend that you kind of learn that it's moles per liter per second, but it could be any amount over any volume and time, meaning that the units of K are exactly the units of the rate, which would make sense if you go back up to the rate law. Now, if it's first order, the units are actually pretty easy. A lot of times they're just per second, but to be honest with you, it's really going to be 1 over some time. So be careful if it was, you know, per minute, per hour, and you'll know that from your graph, because on your graph, your time here would have units. So here they would have seconds, or they would have minutes, or hours, or days. Okay, so be careful. Look at the graph and see what the units of your linear graph are, or the original graph, and then match it up with the right rate order. And then last but not least, the last choice for this type of unit is molarity to the -1 second to the -1. Now, what that means, again, is that you would actually have liters on the top, moles on the bottom, and then seconds. But I would prefer, again, that we realize that this is, again, some, I'm just going to erase this then. It's some volume, and then on the bottom, some amount, and then again per time. So again, just keep, you know, be careful and look for the fact that this could be any volume, liters is common, any amount, moles is common, and then any time, but again, it could be minutes, hours, seconds, days. Okay, and then the new thing here is there is something called an integrated rate law. I'm just going to zoom out so you can see everything here. And the integrated rate law, it's literally what it sounds like. You take your rate law and you integrate it. So it is a calculus-based concept. We're not going to get into that. But the integrated rate law is beneficial because it's in a y equals mx plus b format. And so that's why the linear graph is powerful, because we can find any values we need off of it, interpolating it or extrapolating it. So for example, the integrated rate law for a zero order is just the concentration of your reactant. Well, that's what a lot of times they're going to use A. At some time is going to be equal to -k t, which is time, rate constant times time, and then A naught. A naught is the initial concentration. So it is in a y equals, you know, mx plus b. So again, y equals, and the slope is m, or -k, x, and then plus b is the intercept. So A naught is, or A0 is the initial concentration, and that's this little dot I have at the top here. Let me kind of zoom back out a little bit. This is for the zero order. So your initial concentration would be on this graph or be told to you. For this other one here, this would still be the initial concentration. It would be the initial concentration with the natural log value of it. And then last but not least, this little initial concentration would be 1 over that value. But that's why you want this to be a linear graph so that we can use these integrated rate laws to solve for any interpolated And if, again, a little reminder, interpolate is any, data that's on the graph, and then extrapolate would be any piece of data that's off of the lines that you, or on the line that you collect the data for. All right, so the integrated rate law for a first order is the natural log of A at some time. Again, negative K, which is the slope, and time, T, and then plus the natural log of A naught. And then the last one for a second order reaction is 1 over the concentration at any specific time. And then it's going to be positive K, or they just don't put negative, and then T, and then plus 1 over the 1 over the reciprocal of A naught. And then the other point that's important in this set of notes before we do a practice problem in the next video is you can find the half-life, meaning how much time would it take for half of your reactant to be consumed and made into product, or what concentration would it be at the half-life. So you can do either one. And half-life equations will either be given to you, or you can always solve them, because if you know the initial concentration, you can always use then just half of it. So if you weren't given the equation, I will tell you, you can use any one of these and just put in like 150, meaning not 150, but 100 for like maybe the initial concentration, and then 50 for your half. So you can always just make up numbers, or 1 and 0.5. But so sometimes it's just nice to have the equation. I'm going to put it in green. For the zero order reaction, the half-life is, and they go T1 half, so the time for the reaction to be, half of the reactant to be consumed, is you take the A naught and then 2 times K. So again, you need to know the slope of the graph and your initial concentration, and then you can find when half of it has been consumed and turned into product. And then for a first order, which is the most common one, I'll be honest with you, 0.693 sounds like just a weird random number, but it is actually the natural log of 2, and then it's just over K. So for a first order reaction, the half-life, you just need the rate constant. And think about that. That's something that's going to pop up in questions, is we don't need the initial concentration. And I would kind of pause and have yourself kind of think about that before we get to the example problem. The other thing I want to write down kind of in red is that all radioactive decay reactions where the nucleus is decaying and ejecting alpha, beta, gamma particles, all radioactive decay is first order. And that comes up a lot in different questions, typically. And then last would be, what's the half-life for our second order reaction? And you just do the same thing. T to the 1/2 is 1 over K, and then the initial concentration. So for those two, you do need the initial concentrations to be able to solve for it. But one more time, again, you can always find it yourself, because if you're given the K value, or you have your graph, right? And then if you had, half of it gone, you would just say this could be 1 molar here, and then this would be 0.5, and that would be when, 50% of it has gone away, and then you would just solve for T algebraically. And you're going to see me do something similar to that in the example problem that I have in the video, or the companion video that's going to follow this one. But I wanted to just get you the notes first in this set of time, and then we'll spend the next video on an actual practice problem. All right, well, I hope this helped, and good luck to all of you chemists out there.